Welcome back. So we begin today chapter 20, electrochemistry. Extremely important chapter from the point of view that our technology today is based on batteries. So electrochemistry is going to be the basic that explains that. In particular, when uh, GMC is announcing that by 2025 they're going to have 1 million electric cars on our roads. So this is a technology that is here to stay. The batteries that the cars use are very different to what you're gonna see here, but the principles are the same. So let's begin that. It's a very important knowledge. So to do that, we're gonna attack these concepts. So the first thing we have to learn how to do is to balance oxidation reduction equations. You did that on 1411, but now we're gonna go a lot deeper of what you learned. By the way, we're gonna start the first recording is gonna be a review of what you learned on 1411. Then as we do that, we're gonna learn different terms associated with electrochemistry. We're gonna see how we can construct a basic battery or a galvanic cell. A galvanic cell produces energy. Electrolytic cell consumes energy to perform specific processes. Then we're gonna see how we can determine the voltage or the standard potential of the different batteries or cells that we're gonna be designing. And we're gonna see how all this is gonna relate to the gift-free energy and the equilibrium constant. Everything is just one big concept all linked together. So let's begin with a review about what you learned about oxidation numbers. And as you may remember, oxidation number is just like a counting method we use to keep track of the electrons that are being transferred during a reaction. And we're gonna call that a redox reaction because it involves simultaneously the reduction of one substance and the oxidation of another substance. They are interchanging electrons. So let's begin with the rules. So rule number one: any element by itself, it doesn't matter if it's diatomic, the oxidation number is zero. So any element by itself is always zero, even if it's a polyatomic of the same, so diatomic or sulfur 6, O3, or anything like that. All by itself is zero. Rule number two: if you have an ion, the oxidation number is the same as the charge. But notice that we write it different. The oxidation numbers begin with the symbol and follows with the number. The charge is the number followed by the symbol. So any cation, any anion, the oxidation number is going to be the same as the charge that it carries. So two rules so far. Element by itself, zero. Any ion, the same as the charge. Rule number three: hydrogen is always +1, always between quotations. Oxygen is always -2. Except when we're dealing with peroxide. Peroxide is a polyatomic ion, O2 2-. So whenever we have the peroxide ion, in that case, oxygen is going to be -1 and hydrogen is still +1. So how do we know we have a peroxide ion? Only because you're given the name. If I tell you we're dealing with this compound, which is called hydrogen peroxide, then you know you're dealing with a peroxide because the name tells you so. Another exception to the rule. I mean, the rule is hydrogen is always +1, oxygen is always -2, except when we're dealing with a peroxide, where oxygen, on that case, is going to be -1. And in the case of the hydrogen, if the hydrogen happens to be with a metal, then on that case, hydrogen is -1. It's a hydride. Because remember, hydrogen with only one proton and only one electron can lose the electrons to become H plus, or can gain an electron to be like helium with a full shell and becomes hydride. It can go both ways. So whenever it's with a metal, metals are more to the left on the periodic table, so they're going to be more electropositive. So the metal will have to carry the positive charge. So rule number one, elements by themselves, 0. Ions are the same as the charge. Hydrogen is rule number 3. Hydrogen is always +1, except it's with a metal when it will be -1. Oxygen is always -2, except when it's a peroxide when it's going to be -1. So three rules so far. Rule number 4. Fluorine is always -1, no exception. Fluorine is always -1. All other halogens are also going to be -1, except, and this is a big important except, when we're dealing with interhalogens. Interhalogens are going to be a halogen connected to another halogen. So when you have an interhalogen, both of them cannot be -1 because you cannot have negative and negative. The one that is closer to fluorine, remember fluorine is the most electronegative element in the whole periodic table. The one that is closer to fluorine will be the negative, the other one will have to be positive. So fluorine is always -1. On this case, bromine will have to be +1. Notice that the last rule I'm going to tell you, but you probably have seen the pattern developing, is that compounds have to be 0. So whenever you have a compound, the combination of all of the elements, oxidation numbers have to be 0. So between iodine and chlorine, chlorine will be closer to fluorine, so chlorine will be -1, so iodine will have to be +1. Between bromine and chlorine, chlorine is closer to fluorine, so that will have to be -1, and bromine will have to be +1. And notice that, as always, we always write the more positive first. So whenever we have a compound, the first one is going to be the more positive. So rule number 1, all elements are always 0, even if they're diatomic. Rule number 2, the oxidation number of an ion is the same as the charge. Rule number 3, hydrogen is always positive, oxygen is always 2 negative. Hydrogen can be -1 with a metal, and oxygen can be -1 when it's a peroxide. And then the halogen, fluorine is always -1. And if you have two halogens together, the one closer to fluorine is going to be the -1. Rule number 5, if we're dealing with polyatomic ions, their total charge had to be the same as the charge. The total combination of the oxidation numbers had to be the same as the charge. And for that, we're going to use the rules that we know. So we know that oxygen is always -2. On this case, oxygen is always -2, but there's 4 of them, which means -8. And we know that all the oxidation numbers based on this rule had to give me 2 minus. So the sulfur would have to be +6. So we're using these rules to be able to find out the oxidation number for the elements that do not have a rule. So by knowing that the total polyatomic ion, all the oxidation number combined have to give you the same as the charge, and by using rules number 1, 2, 3, and 4, we can deduct the remaining oxidation number. And that's what we see here. Oxygen is going to be plus 6. What about here? Oxygen is minus 2. There are 2 of them, so that's minus 4. All combined is going to have to be minus 1. So the nitrogen will have to be plus 3. And that's what we get. The next one, oxygen is minus 2, but there are 3 of them, so that's minus 6. All combined, we have to give you minus 1. So the chlorine, on this case, will have to be plus 5. And the last one, once more, oxygen is minus 2, but there are 3 of them, so that's minus 6. All combined have to give you minus 2, so the carbon will have to be plus 4. And that's what we get. And the last rule, rule number 6, you already know that one. The algebraic sum of the oxidation number of all atoms has to be 0. So let's see. So how do we do this? What is the rule for aluminum? We don't have a rule for aluminum. What is the rule for nitrogen? We do not have a rule for nitrogen. However, this is an ionic compound, which means this is aluminum 3 and nitrogen 3 minus. And you get that from the periodic table, right? From knowing that the groups were there. So since this is an ionic compound and we're dealing with ions, then rule number 2 applies. The oxidation number of nitrogen is the same as the charge. The oxidation number of aluminum is the same as the charge. And that's what we are seeing here. So let's go through the list and identify the ionic compounds first. This one is ionic. This one is ionic, metal and non-metal, right? Ionic and ionic. So all of these, all we have to do is find out the ions that we're dealing with. So S2 minus, Ng2 plus, straight from the periodic table. Therefore, the sulfur has to be oxidation number minus 2. The magnesium has to be oxidation number plus 2. On this one here, sodium is plus 1. So hydrogen will have to be minus 1 because rule number 6 tells us that it has to be all zeros, right? So minus 1 plus 1. We know that oxygen is minus 2. There are 2 of them, so that's minus 4. Altogether has to be 0, so the chromium has to be plus 4. And then over here, we know that oxygen is minus 2, and we know that this is carbonate, which is 2 minus, and this is aluminum, which is 3 plus. So the aluminum will have to be plus 3. And there are 3 oxygens. So therefore, this is going to be minus 6. All combined have to give me my charge. So minus 2. So my carbon will have to be +4. Notice that we didn't even have to use these three here because we're just dealing with one of these. The oxidation numbers are not going to change. And let's do the molecular. So phosphorus trichloride, chlorine is always, all halogens, if they are not with other halogens, are going to be -1. There's 3 of them, so this has to be +3. Oxygen is always -2, and hydrogen is always +1. On sulfuric acid, oxygen is -2, and we're dealing, hydrogen is always +1, unless with a metal, right? And since we're dealing with sulfate, and there's 4 oxygens for -8, and altogether it has to give us -2, then the sulfur will have to be +6. So make sure you rewind this and go back and forward until you can agree on all of those numbers, because this is going to be essential for us to be able to move into our course 1412. This is just a review of what you learned on 1411. So how can we use this counting of electrons to decide if we have a reaction or not? That should be an arrow. So what we're going to do, we're going to assign oxidation numbers to each element. Calcium is by itself, so that's going to be 0. Chlorine is by itself, so that's going to be 0. On my products, I have an ionic compound. Chlorine is -1, chloride. There's 2 of them, so calcium will have to be +2, so the whole compound is 0. So we're going to identify the oxidation process, and we're going to identify the reduction process. Remember, most likely you saw this during your 1411 class. Oil rig, meaning oxidation is losing, reduction is gaining, and we're talking about electrons. So when you have something producing electrons, that means it's losing. When you have something with electrons added to it, that's gaining. So gaining is electrons are reactants. Losing or producing is electrons are part of the products. So how can we find out that? So which one is the oxidation? Oxidation is losing. So let's see what happens. The calcium is becoming calcium 2+. So for something to go from neutral to positive, it has to lose electrons. So what I'm going to say is that the calcium becoming calcium 2+, for that to happen, and my equation has to balance on both sides, not only on the amount of atoms, but also on the charge. So right now the charge on the left is 0, the charge on the right is 2+. So the only way we can make that true, 0 equals 2+, is by adding 2 electrons over here. So it's producing electrons, so it's losing electrons, so that would be my oxidation. So this is the way I would write it. So what is happening to the chlorine? The chlorine is going from 0 to -1. So the only way something can go from neutral to negative is by gaining electrons, and that's what we observe here. The chlorine is becoming negative. So on the left side, the total charge is 0. On the right side, the total charge is negative, but there's 2 of them. So the only way we can make the left side equals to the right side is by adding 2 electrons over here. So it's gaining electrons. So the chlorine is gaining 2 electrons, so that's my reduction. So this is definitely a redox reaction because we saw that the element is changing oxidation numbers. We can see that the element is changing oxidation numbers. So every time you can identify a change in the oxidation numbers, we have a redox reaction. And you better be able to identify the reduction and the oxidations because they cannot happen on their own. The electron has to be coming from somewhere. So with that in mind, go ahead and do this daily work, 20.0, because we're still on the review. And when you're done with that, let's go deeper. Let's see if you can apply everything that you already knew for 4311 and that we just reviewed together. How are you going to prove it? You're going to assign oxidation numbers to each one of the elements and see if there was a change or not, following the rules that we discussed. And with that, we come to the end of the review. So when we come back into the next recording, we're going to go straight into 1412, applying everything that we just relearned. So see you soon.